Welcome to This Explainer. A lot of you have been asking for a proper comparison with moving visuals so you can really understand the difference between distance and displacement. Well, you're in exactly the right place. Today, we're diving into the physics of linear motion, kicking things off with a head-to-head matchup of two everyday concepts that we literally mix up all the time. Let's get right into it. So let's start with this totally counterintuitive puzzle straight from our source material. It's kind of going to completely shift how you think about movement. Imagine you're out there giving it your absolute all, sweating through a 160-meter sprint on a straight track. Now, is it possible that a physicist could walk up to you and say, actually, you only moved 40 meters? Sounds totally crazy, right? Well, let's unpack exactly how that is actually possible. To solve this little mystery, let's take a look at this illustration from the text. This is Nina, an athlete running on a straight track. Now, to measure any kind of motion, we first need a fixed reference point, right? We're going to call her starting line the origin, or position 0. Basically, everything we measure from here on out is just going to relate back to this one fixed point on the track. Okay, let's map out her exact journey step by step. At time 0, she's right there at the origin. Then, boom, she takes off running to the right. At 4 seconds, she blows past the 40-meter mark. She keeps pushing all the way out to the 100-meter mark, hitting that at 10 seconds. But wait, she turns around and runs back along that exact same path, finally stopping back at the 40-meter mark at 16 seconds. Now, if we tally up her physical steps, the actual physical ground her feet covered, we get 100 meters moving forward, plus the 60 meters she ran backward from the 100-meter mark back to the 40. So 100 plus 60, that gives us a total of 160 exhausting meters. And that perfectly defines our very first concept, distance. Distance, as you can see, is just the total path traveled between a start and stop point. It's kind of like a pedometer tracking your steps. It literally just keeps adding up the numbers. It only requires a numerical value, what physicists call a magnitude, measured in meters. It absolutely does not care which direction you are running. But hang on a second, let's look at the track again. If we just completely ignore all that back and forth sweating and running, and we just measure the gap between where Nina started at the origin and where she finally stopped to catch her breath, that gap is just 40 meters. And that 40-meter gap is the perfect intro to our second, beautifully precise concept, displacement. Displacement is just the net change in position from start to finish. It totally bypasses the messy journey and just draws a straight line from point A to point B. Oh, and crucially, it requires both a numerical magnitude, so the 40 meters, and a specific direction, like positive or forward. When you see them side by side like this, you can immediately spot the dramatic difference. The distance is that full 160 meters of physical effort, right? But the displacement is literally just a 40-meter net shift in her reality. Seeing this visual comparison really hits the nail on the head as to why we need two entirely different words to describe motion in physics. Okay, so the source text asks us to pause here and ponder an incredible scenario that really puts our understanding to the test. Imagine an athlete running back and forth, just pushing themselves to the absolute limit, but they eventually collapse exactly at the starting line where they began. What is their displacement? Believe it or not, the answer is an astounding 0. Since their start and end points are completely identical, their net change in position is absolutely nothing. I mean, they could have run a full marathon on that track, racking up over 42,000 meters of distance, but to a physicist measuring displacement, it's literally as if they never even got out of bed. So how do scientists actually classify these ideas? Well, as this table breaks down, physicists categorize distance as a scalar quantity. Scalars are simple. They just need a number, a magnitude. Displacement, on the other hand, is a vector. Vectors are a bit more demanding. They require both a magnitude and a direction to give you the complete picture. Now, you might be wondering, do these two rival concepts ever actually agree? Well, yes, but under very strict conditions. The only time distance and the magnitude of displacement are perfectly equal is if you move in a strictly straight line in a single direction and never ever look or turn back. The very second you reverse direction, your distance keeps growing, but your displacement, that starts shrinking. All right, now that we've totally mastered how far things move, let's escalate this head-to-head comparison to see how distance and displacement help us measure how fast things move. Because as it turns out, they spawn two entirely different ways to measure speed. Just like their parent concepts, we get two distinct measurements here: average speed and average velocity. Average speed relies entirely on the total path distance divided by time. Average velocity, however, relies strictly on the net displacement divided by time. Simple enough, right? Let's test this out with a brilliant example directly from the source text. Imagine a boy named Sarang completes a 50-meter round trip in exactly 50 seconds. So he starts at his origin, travels out, and then returns exactly to his starting point within that 50-second time frame. Let's do the math on this. Because Sarang covered 50 meters in 50 seconds, his average speed was a nice, steady 1 meter per second. But take a look at his average velocity. Because he returned to his exact starting point, his net displacement was 0. And well, 0 divided by 50 seconds means his average velocity for the entire trip is mathematically 0. Crazy, right? To wrap up this explainer, let's bring this all back into the real world. The next time you pull up to the gas station, think about this. Is your car's gas tank measuring your physics displacement or your physical distance traveled? I mean, if it measured displacement, every single round trip from your home to the store and back would cost you $0. Unfortunately for our wallets, a real world often runs on distance. But it really makes you wonder, what other everyday measurements are we completely misunderstanding?